remember sitting in an English class a few years ago. We were all going around sharing a family member for whom we were grateful. I remember a boy who raised his hand and shared that he was grateful for his mom, who had been battling breast cancer. After he shared, multiple other people in my class shared that their mothers, aunts, grandmothers, and close family members had also survived or were currently battling breast cancer. It was an eye-opening experience. Until then, I had not realized how prevalent breast cancer was. Yet about 1 in 8 women will develop invasive breast cancer over the course of their lifetime, and every year over 40,000 women in the United States alone will die from breast cancer. But what's even more shocking is that the most significant risk factors for breast cancer are gender, or being a woman, and age, growing older. Most breast cancer is found in women who do not have symptoms. For these reasons, it is difficult for breast cancer to be diagnosed in women early on. But by leveraging machine learning, we can reduce the number of women who are diagnosed with and die from breast cancer. Machine learning allows us to detect the presence of tumors quicker, thus improving the patient's chances of survival. In my project, I built a machine learning model that can classify a tumor as either benign, meaning that the tumor is not harmful, or malignant, a destructive tumor that can grow rapidly and proposes a serious threat to the patient. I used 3 different classification algorithms: a logistic regression model, a decision tree classifier, and a random forest classifier, and compared their accuracy in identifying a tumor as either benign or malignant. And here's how I did it. So the first step in our project is to import our libraries and datasets into our Google Colab notebook, and all of our Python libraries are pre-installed, so all we need to do is import them. And once we've installed our libraries, we can go ahead and import our dataset, and the dataset used for this project will be linked in the description box. And as you can see here, we can go ahead and print the first 7 rows of our data. And here we can see the inputs or the features, which are the columns, and we can see the rows. So each row represents the data of a single patient in the data set. And we kind of want to see what we're working with, right? So here we can see that we have 569 rows, which means we have data from 569 patients, and we have 33 columns or 33 different input features, but we have to keep in mind that not all of these might be valuable. So we can kind of see what null values we have within the columns with this code block here. So if we have null values or empty values, we can get rid of those columns. So we have 33 columns in total, and we can see that in the first 32 columns, we don't have any null values. There are 0 null values in all of these columns, but in our last column, we have 569 null values. So this column is completely empty, and we can get rid of this column. So here we can see that we dropped this column. And so now we still have 569 rows, so we have data from 569 patients still, but we only have 32 columns or 32 different input features now. And next we can go ahead and plot our diagnosis column. So this is just classifying the number of patients with benign tumors and the number of patients with malignant tumors. So we have 357 patients with benign tumors and 212 patients with malignant tumors. And we can also plot this in our count plot here. As you can see, these are the patients with malignant tumors and these are the patients with benign tumors. And we have labeled our y-axis here as count, and this is the diagnosis, the x-axis with malignant and benign. And now we also want to look at the data types of the different features, because our algorithm won't be able to process the data if it's not in a numerical data type. So as we can see here, all of our features are numerical except for a diagnosis feature, which is an object. And so we want to change that into a numerical data type so our algorithm can properly classify it, which we can do here. So as you can see here, using the fit transform method, we can change it into a series of 1s and 0s. So the 1 is a malignant diagnosis, and the 0 is a benign diagnosis. So 1 means that the patient has a harmful tumor, while the 0 means that the patient has a benign tumor, so the tumor is not harmful. So we can do that, and then we can plot the diagnosis once again. So we have Again, 1 is the malignant tumors, so that's the orange. So we can see here that all of the orange plot points are the malignant tumors, and then the blue ones are the benign ones, and we have different plots for different features, and we can do this with all of the columns if we wanted to, but we're only doing this with the first 6 columns, as we can see here. So moving on, we can again look at the first 5 rows of the new data frame, in which all of our data is numerical. So we can keep scrolling. We don't have any null values because we got rid of the last column, which had null values, and we can see here that our diagnosis column also is all numerical instead of an object data type. So moving on, we can make our correlation matrix, and our correlation matrix shows us the influence that the features have on one another. So a correlation of 1 means that there's almost perfect correlation between the features, and a correlation of 0 means that there's no correlation, and if the value is below 0, then we have an inverse correlation. So for example, we can see that the radius mean has more of an influence on the diagnosis of the patient than the smoothness mean, as you can see here. And this is a 1 because obviously the diagnosis has a perfect correlation with itself. And you can also see a somewhat inverse correlation here with the negative values. So we can also visualize our correlation matrix through a heat map, as you can see here. So the fig size just determines the size of the heat map. It's a 10 by 10 heat map, and we can see that the heat map is showing the correlations between the first 12 rows in our data frame. As you can see here, all of the correlation percentages are displayed, and for example, we have obviously 100% correlation with the diagnosis, as obviously the features that are identical to themselves will have 100% correlation. And we can also see some really heavy correlation between, for example, like the radius mean and the area mean, which has a 99% correlation. And we can also see some inverse correlation here, for example, with the fractal dimension mean and the radius mean. We have a negative 31% correlation, which is an inverse correlation. So it's really nice to just visualize the data in this manner and see which features have influences on the others. So now that we have cleaned up our data and visualized it and explored it, we can start preparing it in order to train the model. So first, we need to split our data into independent X and Y data sets. So since the first column is the output of the model, we've established that here as the dependent variable, and then we have the diagnosis of the patient here in column 1, and the remaining 31 features are the inputs of the model. So the model will take in the remaining 31 features and then process them, and then it will give us an output of the diagnosis, which is in column 1. So once we've established these X and Y data sets, we can split up the data into training data and testing data. As we've established here, we have a 25% split between the testing data and training data. So 25% of the data will go to the testing data, and 75% will be used as training data. And we've also established that the random state is equal to 0, which we will touch on later. But basically, the training data is just used to train the model. We will feed the data into the model so that it can learn the relationships between the inputs and the outputs. And the testing data is used after the model is trained. So once we've finished the training and the iterations, we can feed the testing data to the model, and the model will never have seen the testing data during the training. So it's all new data. Now we also want to scale our data before feeding it to the model. And this will allow all of our features or inputs to fit within a certain range, and we can do that using the fit transform method, as you can see here, and then we can pass along our training and testing data. So now we can go ahead and train the 3 different models we are comparing. So we are testing a logistic regression model, a decision tree classifier, and a random forest classifier. So all 3 of these, we are using classification models, and they can be used in this case because we are classifying the features of the patient to result in an output of either a benign tumor or a malignant tumor. And each of these models, when creating a function for them, we can follow a similar structure. So we are importing all 3 of the algorithms from sklearn, and then we can set the random state to be 0, as we established above. And in both the decision tree classifier and the random forest classifier, we will set the criterion equal to entropy, which is just used to calculate the information gain within the nodes of the decision trees. And then we can pass all through the algorithms along our training data, as you can see in like the last line, to see how well they performed, and then print the accuracy of all three of the models. So here we can see the accuracy of the models on the training data, which is the percentage of tumors that it was able to classify correctly. So we can see that the decision tree classifier actually performed the best and classified all of the data accurately, and the random forest classifier performed the second best with an accuracy of 99.5%, and the logistic regression algorithm performed with an accuracy of 99%. So all three of them are performing quite well on the training data, although we can expect the accuracy rate to drop when we run them on the testing data because they have not yet seen the testing data. So in order to run the models on the testing data, we can import a confusion matrix. So the confusion matrix will run the models on the testing data and tell us the number of true positives, true negatives, false positives, and false negatives that the model has classified. So here we can see the accuracy of the models on the testing data. So we can see that the random forest classifier performed the best with an accuracy of 96.5%. The logistic regression model performed with an accuracy of 95%, and the decision tree classifier performed with an accuracy of almost 94%. The confusion matrix also shows us the number of true positives, true negatives, false positives, and false negatives for each of the models. So for example, we can see here that the logistic regression model classified 86 true positives, 50 true negatives, and misclassified 4 tumors as false positives here, and 3 as false negatives. It's also important to note that the accuracy rate of the models on the testing data is a lot more valuable than the accuracy on the training data because the model has seen the training data, it's iterated on it, but all of the testing data is new. It hasn't been exposed to it yet. So how the model performs on the testing data is a more accurate prediction of how it's going to do in the real world. We can also print a classification report for each of the 3 models, which shows us the quality of the predictions that have been made and are also calculated using the true and false, positives and negatives. And you can also see the final accuracy of each of the models here. And so that's how I compared the accuracy of 3 different machine learning models on classifying tumors in breast cancer patients. And none of the models perform perfectly, but we can increase the accuracy of these predictions by continuing to train the model and by tweaking the parameters. And all of the resources that I used in this project will be linked down below. And thank you so much for watching.